Right now, somewhere in this galaxy, there may be a civilization looking at the stars the same way you do, wondering, searching, hoping someone else is out there. They may have telescopes a million years more advanced than ours. They may have cracked physics we have not even imagined yet. And they will never reach us, not because they do not exist, not because they are not trying, but because the universe itself will not allow it. The distance between stars is not just empty space. It is a wall built into the structure of reality. A wall so brutal, so absolute, that even a galaxy teeming with intelligent life could remain permanently, hopelessly, forever alone. What you are about to hear will change how you see the night sky. If this kind of deep science is what you come here for, do me a small favor and hit like and subscribe. It helps more than you think, and it keeps this kind of content coming. Now, are you comfortable? Let's begin. There is a thought experiment that almost everyone performs without realizing it. You look up at the night sky. You see thousands of stars, each one a sun, many of them orbited by planets. You know the galaxy contains hundreds of billions more stars beyond what your eyes can reach. You know the universe has been around for nearly 14 billion years. And somewhere in the back of your mind, a quiet, confident conclusion forms. If life can arise here, it must have arisen elsewhere. And if it arose elsewhere, eventually someone should have shown up. That conclusion feels airtight. It feels like common sense, dressed in scientific clothing. The numbers are so large, the time so deep, the ingredients so common, that the emergence of other intelligent civilizations seems practically guaranteed. And once you accept that, the next step feels equally obvious. They would explore, they would expand, they would build ships, cross the void, and eventually they would find us. This chain of reasoning is one of the most intuitive ideas in all of science. It is also one of the most dangerously wrong. Not because intelligent life cannot exist elsewhere. It very well might. The error is not in the biology. The error is in the assumption that existence leads to contact, that intelligence leads to arrival, that a civilization smart enough to look at the stars is automatically capable of crossing the space between them. That assumption is so deeply embedded in how humans think about the cosmos that most people have never stopped to seriously question it. And the reason they have never questioned it has less to do with physics and more to do with a century of storytelling that quietly rewired our expectations about what the universe allows. Think about every science fiction story you have ever absorbed. Every film, every novel, every video game that involved travel between star systems. In almost all of them, interstellar distance is treated as an inconvenience. Warp drives bend space. Hyperspace lanes cut through dimensions. Wormholes punch holes in the fabric of reality. Cryogenic pods let travelers sleep through the centuries. In fiction, the galaxy is a neighborhood. The stars are destinations. The space between them is a road, long perhaps, but crossable. This framing is so universal across decades of storytelling that it has become invisible. We absorb the assumption without examining it. Faster-than-light travel is not presented as fantasy. It is presented as inevitability, a technology that any sufficiently advanced species would eventually develop, the way humans developed the steam engine or the airplane. Just give them enough time, the universe will yield. The universe does not yield. What almost no piece of popular fiction communicates honestly is this. The distance between stars is not a problem of engineering. It is a condition of reality, a structural feature of the cosmos that operates at a level so fundamental that intelligence, technology, and ambition are almost irrelevant against it. The galaxy is not a neighborhood with bad roads. It is a collection of islands separated by oceans so vast that the word distance barely applies. And those oceans are not made of water. They are made of space-time itself, governed by rules that no amount of cleverness can overwrite. To understand why, you need to see the actual numbers, not the poetic versions. Not the simplified analogies, the real, verified, measured distances that separate one star from another. The nearest star system to our own is Alpha Centauri. It contains 3 stars. The closest of them, Proxima Centauri, sits approximately 4.24 light-years from Earth. A light-year is the distance that light, moving at just under 300,000 kilometers per second, covers in one full year. That translates to roughly 9.5 trillion kilometers per light-year. Multiply that by 4.24, and the distance to Proxima Centauri comes to approximately 40 trillion kilometers. 40 trillion kilometers. That number is so large that it resists comprehension. So let us compress it. Let us shrink the solar system down to something human-scaled and see what happens to the stars. If you place the Sun at one end of a football field and put Earth roughly 2.5 meters away from it, just a couple of strides from the star it orbits, Proxima Centauri would not be at the other end of the field. It would not be across the street. It would not be across the city. At that scale, Proxima Centauri would sit approximately 670 kilometers away. That is the nearest star, the one right next door. The easiest target in the entire galaxy. And at a scale where the distance from Earth to the Sun fits inside a couple of short steps on a football pitch, the nearest neighboring star is further than the drive from London to Edinburgh. The galaxy contains somewhere between 200 billion and 400 billion additional stars beyond that. Most of them are not 4 light-years away. The average distance between stars in our region of the Milky Way is roughly 5 light-years, but the galaxy stretches 100,000 light-years from edge to edge. Stars in the central bulge are packed closer together. Stars in the outer arms are spread further apart. And the nearest large galaxy, Andromeda, is approximately 2.5 million light-years away. These numbers matter because they are not abstractions. They are physical realities that determine what is possible and what is not. And to understand what they mean for travel, we need to look at the fastest object humanity has ever sent into deep space. Voyager 1 launched from Earth on September 5, 1977. It was not designed for interstellar travel. It was designed to study Jupiter and Saturn. But after completing its planetary mission, it kept going. It is still going. As of early 2026, Voyager 1 is approximately 173 astronomical units from Earth. An astronomical unit is the distance from Earth to the Sun, roughly 150 million kilometers. So, Voyager 1 is about 25.8 billion kilometers from home. That sounds far. It is far by every human standard. It is the most distant object humanity has ever created. In November of 2026, it will cross a historic threshold. It will be 1 full light day from Earth. That means a signal traveling at the speed of light, the fastest speed anything in the universe can move, will take 24 hours just to reach the spacecraft from mission control. A round-trip communication will take 2 full days. 49 years of flight to reach 1 light day. Now consider this. Proxima Centauri is not 1 light day away. It is approximately 1,550 light days away. More than 4 light years. At Voyager, one's current velocity of roughly 17 kilometers per second reaching Proxima Centauri would take over 73,000 years. That is not a round trip, that is one way. 73,000 years of continuous flight just to reach the nearest star. For context, 73,000 years ago, anatomically modern humans were sharing the planet with Neanderthals. The entirety of recorded human civilization, every empire, every monument, every book ever written, fits inside the last 5,000 years. Voyager would need more than 14 times that span just to drift to the closest neighboring sun, and it would arrive dead. Its radioisotope thermoelectric generators are fading. As of 2026, only 2 scientific instruments remain operational. Engineers expect the spacecraft to lose the ability to return any data at all within the next few years. Its power source will be effectively exhausted by the mid-2030s. Long before it reaches even 1% of the distance to Proxima Centauri, Voyager 1 will become a silent, frozen artifact, tumbling through the void, carrying a golden record that no one will ever play. This is the fastest thing we have ever built, and against the distance to the nearest star, it is standing still. The obvious response is that Voyager was never designed for interstellar travel. It uses 1970s propulsion technology. Surely a more advanced civilization, or even a future version of humanity, could do better. Build faster ships, use better engines, close the gap. This is where the physics turns cruel. The speed of light is not a speed record. It is not a barrier waiting to be broken by a smarter species with better funding. It is a fundamental property of the structure of spacetime, confirmed by over a century of experimental physics. Albert Einstein's theory of special relativity, published in 1905 and verified countless times since, describes exactly what happens as an object with mass approaches the speed of light. Its relativistic mass increases, not metaphorically, physically. The energy required to accelerate it further grows not linearly, not even quadratically, but asymptotically. It curves upward toward infinity. This means that the closer you get to light speed, the more energy each additional increment of velocity demands. At 50% of the speed of light, the energy cost is already enormous but technically calculable. At 90%, it has grown so severe that accelerating even a modest payload requires energy output on the scale of what entire civilizations consume. At 99%, the energy required for further acceleration exceeds the total energy output of stars. At the speed of light itself, the energy required is literally infinite. Not practically infinite, mathematically infinite. No finite amount of energy, no matter how large, can accelerate any object with mass to the speed of light. This is not a gap in our technology. It is a law of the universe, and it applies equally to every civilization that has ever existed or ever will exist, anywhere in the cosmos, regardless of how intelligent they are, regardless of how advanced their engineering becomes. The speed of light is not just a limit on how fast you can travel. It is a limit on how fast anything in the universe can happen. It is the speed at which causality propagates, the speed at which information moves, the speed at which gravity communicates changes. Nothing outruns it, because it is not a speed in the ordinary sense. It is a conversion factor between space and time, woven into the geometry of reality at its most fundamental level. Asking a civilization to exceed the speed of light is not like asking them to break the sound barrier. It is like asking them to build a triangle with 4 sides. The request does not describe something difficult. It describes something that does not exist. What this means for interstellar travel is devastating. Even if a civilization somehow assembled the energy to accelerate a spacecraft to 10% of the speed of light, which is itself an almost unimaginable achievement, the trip to Proxima Centauri would still take 42 years one way. A star 50 light-years away would take 500 years. A star at the center of the galaxy, roughly 26,000 light-years distant, would take 260,000 years. These are the travel times with the speed of light as a hard ceiling, and 10% of that ceiling as an already heroic velocity. And we have not yet touched the energy cost. The tyranny of the rocket equation governs every spacecraft that carries its own fuel. The equation is simple but merciless. To accelerate a payload to a given velocity, you need fuel. But the fuel has mass, and that mass must also be accelerated, which requires more fuel, which has more mass. The relationship is exponential. For chemical rockets, the exhaust velocity is roughly 4.5 kilometers per second. To reach even a small fraction of light speed using chemical propulsion, the fuel mass required would exceed not just the mass of the spacecraft, not just the mass of the Earth, but the mass of the observable universe. That is not an exaggeration. It is a mathematical consequence of the exponential function applied to the ratio between required velocity and exhaust velocity. Nuclear propulsion improves the numbers but does not escape the trap. Nuclear thermal rockets achieve higher exhaust velocities. Nuclear pulse propulsion, the concept behind Project Orion, would detonate nuclear bombs behind a massive pusher plate to achieve velocities of a few percent of light speed. Fusion propulsion, if it could be made to work, offers still higher performance. But every one of these systems confronts the same exponential wall. The fuel-to-payload ratio grows so steeply that for any velocity above a few percent of light speed, the mass of fuel required dwarfs the mass of anything useful you could carry. A peer-reviewed paper on radiation-powered interstellar rockets calculated that sending a 100-ton spacecraft to the nearest star system using the most efficient propulsion theoretically possible, a matter-antimatter annihilation drive converting nearly 100% of mass to energy, would require more than 15 times the current total energy production of the entire world. That is, for the most efficient engine physics permits aimed at the closest star, carrying a payload that would barely qualify as a large aircraft. Scale the mission to anything resembling a crewed vessel, and the energy demands become civilizational. Scale it to a fleet, and they become stellar, and even that calculation assumed the most efficient engine that physics permits. It is worth pausing on what that engine actually requires, because the gap between theoretical efficiency and practical reality is not a crack, it is a canyon. A matter-antimatter annihilation drive converts mass directly into energy with nearly perfect efficiency. When a particle of matter meets its antimatter counterpart, both are annihilated, and their entire combined mass is released as energy in the form of high-energy photons or particle-antiparticle jets. The conversion rate approaches 100%. Compare that to nuclear fission, which converts roughly 0.1% of its fuel mass into energy, or nuclear fusion, which manages roughly 0.7%. Antimatter propulsion is not incrementally better than nuclear alternatives. It is orders of magnitude better. It is, by a wide margin, the most energetically efficient reaction known to physics, which is precisely why it appears in every serious theoretical study of interstellar propulsion, and precisely why every serious theoretical study immediately collides with the same insurmountable problem. We cannot make the fuel. The European Organization for Nuclear Research, CERN, operates the most sophisticated particle physics facility on Earth. Among its many functions, it produces small quantities of antimatter for experimental purposes. Over its entire operational history spanning decades, CERN has produced a total of approximately 20 nanograms of antimatter, primarily antiprotons and positrons, 20 billionths of a gram, accumulated across years of operation by one of the most expensive and complex scientific instruments ever built. A single interstellar mission using antimatter propulsion, even a modest one aimed at the nearest star with a small payload, would require kilograms of antimatter at a minimum. Some estimates for crewed missions run to tens or hundreds of tons. The gap between what we can produce and what we would need is not a factor of 10 or 100. It is a factor of trillions. At CERN's current production rate, manufacturing 1 gram of antimatter would take on the order of 1 billion years, a span roughly a tenth of the entire age of the universe, for a single gram of fuel that would not come close to powering a crewed interstellar mission. And the energy cost of production compounds the absurdity. Creating antimatter requires pouring in at least as much energy as you will eventually extract from annihilating it, and in practice far more, because the production process is extraordinarily inefficient. Current methods capture only a tiny fraction of the antiparticles generated in high-energy collisions. The rest are lost. The energy invested in producing usable antimatter exceeds the energy recovered from burning it by factors of billions. This is not a temporary limitation of our technology. It reflects something deeper about the physics of antimatter production. Creating antiparticles requires concentrating enough energy in a small enough volume to conjure particle-antiparticle pairs from the quantum vacuum. This is inherently expensive in energy terms. There is no known shortcut, no clever catalytic process, no undiscovered natural reservoir of antimatter waiting to be tapped. The universe is overwhelmingly composed of matter. Antimatter exists in nature only in vanishingly small quantities, produced fleetingly in high-energy cosmic events and annihilated almost instantly upon contact with surrounding matter. So the most efficient propulsion system that physics allows runs on a fuel that cannot be produced in useful quantities by any known method, at any plausible cost, on any realistic timescale. The theoretical ceiling of engine performance is real. The floor of fuel availability sits so far below it that the ceiling is irrelevant. It is like designing a car that runs on diamond dust and then discovering that the entire planet contains less diamond dust than the engine needs for a single trip across town. This matters because antimatter propulsion is not one option among many. It is the best option. Every other propulsion concept falls below it in efficiency. If the best possible engine cannot be fueled, then every engine below it faces even harsher versions of the same energy and mass constraints. The hierarchy of interstellar propulsion concepts is not a ladder reaching toward feasibility. It is a ladder leaning against a wall that has no top. The point is not that we cannot do it today. The point is that the energy costs are not a function of our primitiveness. They are a function of the physics. A civilization 1,000,000 years more advanced than ours faces the same speed of light, the same relativistic mass increase, the same exponential fuel requirements. They might manage those requirements more cleverly. They might access energy sources we cannot imagine, but they cannot repeal the laws that generate the requirements in the first place. This is the fracture line where intuition breaks. The human mind is built to solve problems by extrapolating from past success. We went from horses to cars to airplanes to rockets in a few centuries. The pattern feels like it should continue, faster and faster, further and further, until the stars are within reach. But interstellar distance does not sit on that curve. It is not the next step up from interplanetary travel. It is a categorical leap into a regime where the numbers change their character entirely. The distance from Earth to Mars is, at its closest, roughly 55 million kilometers. A fast transit with current technology takes about 7 months. The distance from Earth to Proxima Centauri is roughly 40 trillion kilometers. That is not 10 times further than Mars. It is not 100 times further. It is more than 700,000 times further. The gap between planetary travel and interstellar travel is not a slope. It is a cliff, and at the bottom of that cliff, the physics changes. Speeds that are adequate for crossing a solar system become laughably insufficient for crossing to another star. Energy budgets that can sustain a Mars mission become irrelevant fractions of what an interstellar crossing demands. And this is only the beginning of the problem. Because everything we have discussed so far, the distance, the speed of light, the energy cost, the rocket equation, is just the first layer. It is the barrier you hit before you even begin to consider what happens to a spacecraft and its passengers during a journey that lasts decades, centuries, or millennia. The radiation, the shielding, the mechanical degradation, the biological toll, the communication silence, The slow, grinding reality of crossing a void so enormous that the ship becomes its own world, cut off from everything it left behind, sustained by nothing but what it carries. The intuition that aliens should have visited by now rests on an assumption so deep that most people never examine it. The assumption that the universe is navigable, that space is a medium through which civilizations can move. That the distance between stars, while large, is fundamentally the same kind of problem as the distance between continents, just scaled up. It is not the same kind of problem. It is not scaled up. It is transformed. The rules change. The mathematics change. The relationship between effort and result changes. And what waits on the other side of that transformation is not a harder version of a familiar challenge. It is a wall built into the geometry of the cosmos, made of light speed limits and exponential energy curves, and the sheer, crushing, implacable vastness of the space between suns. The question is not whether aliens are smart enough to solve this. The question is whether there is a solution to find. And everything we know about physics, confirmed by every experiment, every observation, every measurement ever taken, points in one direction. The universe is not an open road. And what comes next will show you exactly how locked the gates really are. We have laid out the wall, the speed of light, the exponential energy curve, the raw, implacable distance between one star and the next. But walls can sometimes be climbed. They can be tunneled under. They can be chipped away at with patience and ingenuity. The question that hangs over everything discussed so far is whether the wall blocking interstellar travel has any cracks in it at all. Whether some combination of propulsion, engineering, and endurance could thread a spacecraft through the gap between here and there. The answer requires going deeper than distance and speed. It requires looking at the specific physical mechanisms a spacecraft would need to survive, not as abstract categories, but as interlocking constraints that tighten around each other like the links of a chain. What follows is not a list of problems. It is a cascade. Each barrier feeds the next. Each solution creates a new cost. And by the end, the picture that emerges is not of a difficult engineering challenge waiting for a breakthrough. It is of a system designed, if that word can be used for something so impersonal, to resist transit at every level. Start with propulsion, because propulsion is where every interstellar mission begins and where most of them die. We established that chemical rockets cannot reach interstellar velocities. The exhaust velocity is too low. The fuel mass required too catastrophic. But chemical rockets are the crudest option available. Humanity has conceived of far more powerful systems, and some of them have been studied in serious engineering detail. The question is whether any of them actually solve the problem or merely shift it into a different shape. Nuclear thermal propulsion heats a propellant, typically hydrogen, by passing it through a nuclear reactor core. The exhaust velocity roughly doubles compared to the best chemical engines. This improves the fuel ratio considerably for missions within the solar system. For interstellar distances, it barely registers. Doubling the exhaust velocity does not halve the fuel requirement. The rocket equation is exponential. Doubling the exhaust velocity for a mission requiring a velocity change of 10,000 kilometers per second reduces the fuel ratio from one impossibly large number to a slightly less impossibly large number. The destination remains out of reach. Nuclear pulse propulsion is more dramatic. Project Orion, studied by the United States government in the late 1950s and early 1960s, proposed detonating nuclear bombs behind a massive pusher plate to accelerate a spacecraft. The concept is sound. The physics works. Orion-class vehicles could theoretically achieve velocities of 3 to 5% of the speed of light, depending on the design. At 3%, the trip to Proxima Centauri takes roughly 140 years. That is within the outer boundary of what a multi-generational mission might attempt, though the engineering and human challenges of such a mission are staggering on their own. But Orion has a cost that goes beyond engineering. The vehicle requires thousands of nuclear detonations. The smallest proposed design called for 800 bombs. Larger interstellar variants would need hundreds of thousands. Each detonation produces an electromagnetic pulse, a burst of radiation, and a spray of fission products. The ship must survive every single one of them across a sequence lasting years. The pusher plate must absorb repeated nuclear blasts without cracking, warping, or eroding. The shock absorbers connecting the plate to the crew compartment must dampen forces that would otherwise crush every occupant into paste. No prototype was ever built. No component was ever tested at full scale. The project was shelved not because the physics failed, but because the engineering requirements dwarfed anything humanity had ever attempted, and the political environment made testing nuclear propulsion systems in space effectively impossible. Fusion propulsion represents the next tier. Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, proposed a spacecraft powered by inertial confinement fusion, igniting pellets of deuterium and helium-3 with electron beams to produce thrust. The design called for a two-stage vehicle, massing roughly 54,000 tons at launch, carrying 50,000 tons of fuel. It would accelerate to roughly 12% of the speed of light and reach Barnard's star, approximately 6 light-years away, in about 50 years. But it could not slow down. Daedalus was designed as a flyby mission. It would scream past its target at 36,000 kilometers per second, gathering data for a few hours before continuing into the void forever. The reason it could not slow down is instructive. Decelerating from 12% of light speed requires almost as much energy as accelerating to it. Carrying enough fuel to both accelerate and decelerate would roughly double the initial mass, which would require more fuel to accelerate that additional mass, which would require more fuel still. The exponential curve bends upward so steeply that a round trip, accelerating, decelerating, stopping, accelerating again, and decelerating at the destination, would require a starting mass so enormous that no plausible fuel source could provide it. Daedalus solved this by not stopping. It accepted that the mission was a one-way dash, a glance at a star system from a spacecraft moving so fast it would cross the entire target zone in hours. The deceleration problem deserves more weight, because it separates two fundamentally different categories of mission, and only one of them constitutes anything resembling contact. A flyby is not a visit. A spacecraft that screams through a star system at 12% of the speed of light is moving at roughly 36,000 kilometers per second. At that velocity, the entire habitable zone of a sun-like star, the region where Earth-like planets could orbit, is crossed in a matter of hours. The time available for close observation of any single planet is measured in minutes. The spacecraft cannot enter orbit, it cannot land, it cannot deploy instruments to the surface. It cannot study atmospheric chemistry over seasonal cycles or search for surface features that require sustained observation. It collects what it can in a brief window and then continues into the void, carrying its data away from the target at a velocity that makes return impossible. This is not a theoretical limitation of one particular mission design. It is a structural consequence of the exponential mathematics we encountered with Daedalus, carried to its precise conclusion. The numbers make it vivid. If a ship requires a fuel-to-payload ratio of 10:1 to accelerate to its cruising velocity, then adding deceleration capability does not simply double the ratio to 20:1. The rocket equation is exponential, not linear. Every kilogram of deceleration fuel must itself be carried through the acceleration phase, which demands its own additional fuel, which demands still more. The result is that the total fuel ratio for a mission that both accelerates and stops is not twice, the one-way ratio. It is the one-way ratio squared. A mission with a one-way fuel ratio of 10 to 1 becomes an arrive and stop ratio of roughly 100 to 1. A 1-to-1 ratio of 50 to 1 becomes 2500 to 1. The numbers become absurd almost immediately. This is why Project Daedalus was designed as a flyby. This is why Breakthrough Starshot is designed as a flyby. This is why virtually every propulsion study that produces plausible interstellar velocities ends with the same concession. The ship can get there, perhaps, but it cannot stop. And a mission that cannot stop is not contact. It is observation from a platform moving so fast that the target is a blur. It might confirm the existence of a planet. It might detect atmospheric gases. It might photograph surface features at resolution limited by the absurd closing velocity, but it cannot interact. It cannot land. It cannot stay. It passes through, and the moment of closest approach, the only moment when the instruments are close enough to gather meaningful data, lasts less time than a commercial airline flight. For a mission to constitute genuine contact, the kind that the Fermi paradox implicitly assumes should have happened, the spacecraft must arrive and remain. It must enter orbit or land. It must operate at the destination for an extended period. And achieving that requires carrying enough fuel to decelerate from interstellar velocity to orbital velocity, a delta-v budget so large that it effectively doubles the already crushing energy requirements described earlier in this section. The deceleration problem does not merely add difficulty to interstellar travel. It transforms the category of mission from theoretically conceivable to practically excluded for any payload mass larger than a paperclip. This is the fundamental character of every propulsion concept that has ever been seriously studied for interstellar travel. Each one involves a trade: speed for fuel mass, deceleration for even more fuel mass, stopping ability for mission type, crew for payload, duration for survivability. And at every point in the trade, the numbers push back with the full weight of exponential mathematics. The most ambitious real-world attempt to address these constraints is Breakthrough Starshot. Announced in 2016, with $100 million in initial funding from investor Yuri Milner, the project proposed something genuinely different. Instead of carrying fuel, the spacecraft would be pushed by light. A ground-based laser array producing roughly 100 gigawatts of power would fire a concentrated beam at a light sail attached to a gram-scale nanocraft, a chip-sized probe weighing a few grams at most. The laser would accelerate the sail to roughly 20% of the speed of light within minutes. At that velocity, the probe would reach the Alpha Centauri system in approximately 20 years. The concept is elegant because it sidesteps the rocket equation entirely. The fuel, in this case photons from a laser, stays on the ground. The spacecraft carries nothing but a sensor, a communications laser, and the sail itself. No exponential mass problem. No fuel that must accelerate fuel. Just light pushing a whisper-thin mirror through the void. But elegance and feasibility are not the same thing. The engineering challenges are immense, and many remain unsolved. The sail must survive acceleration forces of roughly 60,000 times Earth gravity for the few minutes it is under the beam. It must remain stable under a 100 gigawatt laser without tearing, melting, or tumbling out of alignment. Researchers have made meaningful progress on sail materials. A 2025 study demonstrated pentagonal photonic crystal mirrors using optical lithography that reduced sail fabrication costs by a factor of roughly 9,000. These sails achieved 99% reflectivity at target wavelengths using silicon nitride films just 200 nanometers thick. But building a centimeter-wide laboratory mirror and building a 4-meter sail that can hold its shape under a beam powerful enough to push it to a fifth of the speed of light are separated by an engineering gulf that has not yet been crossed. The laser array itself presents challenges that border on the surreal. 100 gigawatts is roughly the total electrical generating capacity of a mid-sized country. The beam must remain focused on a sail that is accelerating away from Earth at thousands of kilometers per second, maintaining targeting precision across tens of thousands of kilometers of distance while compensating for atmospheric distortion in real time. Proposals exist for orbital corrections using satellite relays, but none have been prototyped. Then there is the data return problem. A gram-scale probe arriving at Alpha Centauri carries a tiny onboard laser for communication. That laser must transmit usable data across 4.24 light-years of space to a receiver on or near Earth. The signal will be so faint by the time it arrives that detecting it will require receiver arrays larger and more sensitive than any currently in existence. And even if the data arrives, it will take over 4 years to do so. The probe cannot slow down. It will pass through the Alpha Centauri system at 20% of light speed, covering the region of scientific interest in a matter of hours. It gets one chance. If the instruments fail, if the aim is slightly off, if the communication laser is damaged by a dust grain during the 20-year transit, the mission returns nothing. And as of 2025, the Breakthrough Starshot project itself appears to have stalled. A Scientific American investigation reported that the initiative is on indefinite hold, with key personnel declining interviews and a promised progress report failing to materialize. The project has not been formally cancelled, but its future is described as murky. The engineering challenges, while not theoretically insurmountable, have proven resistant to the timeline and budget originally envisioned. This is perhaps the most telling detail of all. The most creative, most physically grounded, most well-funded interstellar propulsion concept in human history, one that does not even attempt to carry a crew or slow down at its destination, has struggled to move beyond the conceptual phase after a decade of effort. This is what propulsion looks like when measured against interstellar distance, not impossible in every theoretical sense, but so punishingly hard, so constrained by exponential costs and cascading engineering demands, that even the cleverest approaches buckle under the weight of the actual numbers. And propulsion is only the beginning, because even if a spacecraft achieves the velocity it needs, it must then survive what it flies through. The space between stars is not empty. It is close to empty, and the difference between those two things becomes lethal at high speed. The interstellar medium consists primarily of hydrogen, roughly 1 atom per cubic centimeter in the local region of our galaxy. There are also helium atoms, trace amounts of heavier elements, and microscopic dust grains scattered through the void. At rest, or at the gentle velocities of Voyager-class spacecraft, this material is irrelevant. A few atoms per cubic centimeter encounter a spacecraft with the force of nothing at all. At relativistic speeds, the math changes catastrophically. When a spacecraft moves at 10% of the speed of light, it covers roughly 30,000 kilometers every second. Every cubic centimeter of space it passes through delivers its sparse collection of hydrogen atoms to the hull, but each of those atoms now carries kinetic energy proportional to the square of the relative velocity. At 10% of light speed, a single hydrogen atom strikes the hull with an energy of roughly 5 million electron volts. That is the energy range of particles produced by medical cyclotrons, machines specifically designed to generate radiation for cancer treatment. Each atom becomes a miniature bullet carrying nuclear-scale energy. The flux is not dense in absolute terms, but it is continuous. Over the cross-sectional area of a realistic spacecraft moving at 10% of light speed, the number of hydrogen impacts per second produces a radiation dose rate comparable to standing inside an unshielded nuclear reactor. At 20% of light speed, the energy per atom quadruples. At 50%, it increases by a factor of 25 relative to 10%. The interstellar medium, which is harmless at low speeds, becomes a directed particle beam at relativistic velocities. The ship flies into its own radiation bath, generated not by any onboard system, but by the simple act of moving fast enough through material that is technically almost nothing. There is a concept that was once considered the most elegant solution to the fuel problem, and understanding why it fails reveals something important about the depth of the constraints involved. In 1960, physicist Robert Bussard proposed what became known as the Bussard ramjet. The idea was seductive in its simplicity. The interstellar medium contains hydrogen. Hydrogen is fusion fuel. Instead of carrying all your fuel from the start, build a spacecraft with an enormous magnetic scoop at the front. As the ship moves through space, the scoop funnels interstellar hydrogen into an onboard fusion reactor. The reactor burns the hydrogen for thrust. The faster you go, the more hydrogen you scoop, the more thrust you produce. In theory, the ship accelerates continuously without ever running out of fuel, because the fuel is the space you are flying through. For decades, the Bussard ramjet was the most physically grounded concept for continuous acceleration interstellar travel. It appeared in serious engineering discussions. It inspired entire subgenres of science fiction. It seemed to offer a way around the tyranny of the rocket equation because the fuel was not carried at launch. It was collected en route. The physics destroyed it. The problem is drag. The magnetic scoop that collects interstellar hydrogen does not do so for free. The hydrogen atoms in the interstellar medium are essentially stationary relative to the ship. Scooping them up means accelerating them from rest to the ship's velocity before they can be fed into the reactor. At low speeds, this cost is manageable. At relativistic speeds, the energy required to accelerate the incoming hydrogen to the ship's frame of reference exceeds the energy gained by fusing it. The scoop becomes a brake. The faster the ship flies, the harder the interstellar medium pushes back against it. Detailed analyses published in peer-reviewed astrophysics journals across the 1970s and 80s confirmed this conclusion from multiple angles. The drag, produced by the interaction between the magnetic scoop field and the ionized component of the interstellar medium, creates a force that scales with velocity in a way that overwhelms the thrust produced by fusion at any speed above. A few % of the speed of light. The ramjet does not accelerate to relativistic velocity. It reaches a terminal speed at which drag and thrust balance, and that speed is far too low for practical interstellar transit. Variations have been proposed. Pre-ionizing the hydrogen ahead of the ship with a forward-mounted laser, using the scooped hydrogen only as reaction mass, not as fusion fuel. Narrowing the scoop to reduce drag while accepting a lower collection rate. None of them resolve the fundamental tension. The interstellar medium is too thin to provide abundant fuel and too resistant to collection at high speed to serve as a free propellant source. The fuel is there, spread across light years of space, and it is inaccessible precisely when you need it most. The Bussard ramjet matters to this story not because it was ever likely to work, but because it represents the most creative attempt to circumvent the deepest structural constraint on interstellar propulsion, and it failed on the physics, not on the engineering, not on the funding, on the physics. The universe placed the fuel between the stars and then made it impossible to collect at the speeds required to use it. Shielding against this bombardment is not straightforward. Passive shielding, placing mass between the radiation source and the crew, works up to a point. But high-energy protons and heavier nuclei interact with shielding material in ways that create secondary radiation. When a fast proton strikes an atom of iron or aluminum, it can shatter the nucleus and produce a spray of neutrons, gamma rays, and lighter nuclear fragments. These secondary particles are often more penetrating than the original radiation. They scatter in all directions, turning the shield itself into a radiation source. The thicker the shield, the more secondary particles it generates. There is a point of diminishing returns beyond which adding more material makes the interior environment worse, not better. NASA has studied this problem extensively in the context of Mars missions, which would expose astronauts to galactic cosmic rays for periods of roughly 2 to 3 years. Even on that timescale, radiation exposure remains one of the most critical unsolved barriers to human deep space travel. Galactic cosmic rays, high-energy protons, and heavy nuclei, accelerated by distant supernova shockwaves, penetrate deeply into spacecraft structures and human tissue. They break DNA strands, they kill cells. They damage the central nervous system in ways that can degrade cognitive function, memory, and behavior. Long-duration exposure increases the risk of cancer, cardiovascular disease, cataracts, and degenerative tissue conditions. A 2026 presentation at a UC Davis Astronomy on Tap event by physicist Daniel Seabra, who chairs the UC Davis Department of Physics and Astronomy and studies high-energy nuclear collisions relevant to NASA's radiation shielding challenges, emphasized that galactic cosmic ray shielding remains an active and unsolved area of research, even for missions within the solar system. The challenge is not merely absorbing radiation, but managing the cascade of secondary particles that thicker shielding produces. Active shielding concepts, using powerful magnetic fields to deflect charged particles before they reach the hull, have been proposed but require superconducting magnets of enormous size and power. Current designs can deflect lower-energy solar particles, but struggle against the highest-energy galactic cosmic rays, which carry so much momentum that magnetic fields strong enough to turn them would require power systems far beyond anything yet engineered. For an interstellar mission lasting decades or centuries, these problems do not simply persist, they compound. A crew exposed to elevated radiation for 5 years accumulates a measurable increase in cancer risk. A crew exposed for 50 years accumulates a near certainty of radiation-induced illness across the population. A crew exposed for 500 years, the timescale of even a moderately fast interstellar transit to a star beyond the nearest few, would require either shielding solutions that do not currently exist in any form or biological interventions capable of repairing radiation damage continuously across generations. And the radiation from the interstellar medium is only half the problem. The dust is the other half. Interstellar dust grains are tiny, typically a micrometer or less in diameter. They are composed of silicates, carbonaceous material, and ice. At rest, they are invisible and irrelevant. At relativistic speeds, they become destructive in a way that defies intuition. A 1 micrometer grain at 10% of light speed carries less than a joule of total kinetic energy. That sounds harmless. It is not. Because that energy is delivered to an impact area measured in millionths of a meter, the energy density at the point of contact is extraordinary. The grain does not bounce off the hull the way a pebble bounces off a car windshield. It vaporizes on contact, along with a plug of hull material many times its own volume, creating a microscopic crater surrounded by fractured and weakened substrate. Each impact is a tiny explosion at the molecular level, melting and restructuring the surface in ways that accumulate with every kilometer traveled, and you cannot see them coming. Dust grains at those sizes are undetectable at any useful range by any sensor technology that exists or is plausibly foreseeable. A spacecraft moving at relativistic speed has no ability to dodge, deflect, or even anticipate individual grain impacts. It simply absorbs them. Over the course of a multi-decade journey across light years of space, millions of these microscopic detonations pockmark every forward-facing surface. Sensors lose clarity, optical coatings degrade, structural materials weaken as crater after crater removes mass and introduces stress fractures. A sail, if one is used, accumulates perforations that reduce its reflective area and compromise its structural integrity. This is not a hypothetical concern. It is a measured property of the interstellar medium applied to known hypervelocity impact physics. The damage is statistical, not dramatic. No single grain will destroy a spacecraft. But across decades of flight, the cumulative erosion of forward-facing surfaces progresses with a steadiness that no maintenance crew can fully counteract, because the damage source is the direction of travel itself. Now, layer another problem on top of propulsion, radiation, and erosion. Communication. A spacecraft that departs Earth on an interstellar mission does not maintain a conversation with home. It sends messages. Those messages travel at the speed of light. To Proxima Centauri, the nearest star, a one-way signal takes 4 years and 3 months to arrive. A round-trip exchange takes 8.5 years. That is the best case. The absolute minimum delay for the closest possible destination. For a star 50 light-years away, a one-way signal takes half a century. For a star 500 light-years away, a one-way signal takes 500 years. The crew that sends a message from that distance will be dead before the reply arrives. Their children will be dead. Their grandchildren's grandchildren will be dead. The reply will arrive at a ship that has been in flight for a millennium, crewed by people who have no living memory of the civilization that launched it. This is not merely an inconvenience. It is a structural severance. A spacecraft that cannot communicate with its origin in real time is, in every practical sense, alone. It cannot request help. It cannot receive updated navigation data. It cannot report emergencies or receive solutions. If a critical system fails, the crew must fix it with what they have or die. If a medical crisis arises, there is no consultation possible. If a decision must be made about whether to change course, abort, or continue, the decision belongs to the people on the ship and no one else, because the people on Earth, who might have an opinion, will not hear about the situation for years or decades, and their response will arrive years or decades after that. Every military commander, every expedition leader, every project manager in human history has operated within a communication framework where information could flow between the field and headquarters within hours, days, or at worst weeks. Interstellar travel eliminates that framework entirely. The ship is not a remote outpost. It is a sovereign entity, operating without oversight, without resupply, without external input of any kind, for the duration of a journey that exceeds the lifespan of every person aboard. Now hold all of these problems in your mind at once, not as a list. As a system, the spacecraft must achieve a velocity high enough to reach its destination within some meaningful time frame. Achieving that velocity requires either enormous fuel mass or an external propulsion system of unprecedented scale. The fuel mass increases the total mass that must be shielded. The shielding mass increases the total mass that must be propelled. The propulsion energy increases the infrastructure required before launch. The higher the velocity, the worse the radiation from the interstellar medium becomes. The worse the radiation, the more shielding is needed. The more shielding, the more mass. The more mass, the more fuel. The more fuel, the more mass. Every solution wraps back into the problem it was meant to solve, and those are only the physical constraints. The spacecraft must also carry enough food, water, and breathable atmosphere for a crew surviving years, decades, or centuries. It must carry enough spare parts and raw materials to repair every system that might fail. It must carry enough genetic and cultural diversity to maintain a viable population if the journey spans generations. It must carry enough computational and manufacturing capacity to address problems that no one predicted before launch, because no one can predict every failure mode across timescales that exceed the operational life of any machine ever built. The ship must also manage its own waste heat. Every energy conversion process generates heat. In the vacuum of space, heat can only be radiated away, not convected or conducted to a surrounding medium. A ship with a nuclear reactor for power, life support systems for a crew, and active shielding against radiation produces heat continuously. The radiators required to shed that heat add surface area, add mass, and add vulnerability to dust erosion and radiation damage. A ship that cannot shed its waste heat fast enough will cook its own crew, not from any external source, but from the accumulated byproduct of simply being alive and operating in a sealed vessel moving through a vacuum. This is the machinery of impossibility. Not a single wall. A web of interlocking constraints that tighten against each other at every point. Pull on one thread and three others draw taut. Solve one problem and two new ones crystallize from the solution. It is not that no individual barrier is absolutely insurmountable. It is that they do not stand alone. They form a structure, and the structure resists with a coherence that feels almost architectural, as though the universe built the space between stars not merely as distance but as a gauntlet, a sequence of tests so tightly linked that passing one makes the next more punishing. And, critically, these constraints are not human. They are not artifacts of our particular level of technology or our biological fragility. They arise from physics. Any civilization, no matter how old, no matter how intelligent, no matter how different its biology, faces the same speed of light, the same interstellar medium, the same exponential fuel costs, the same radiation environment, the same communication delays, the same thermodynamic limits on waste heat rejection. An alien species with silicon-based biochemistry still takes radiation damage from relativistic protons. A machine intelligence with no biological crew still degrades from microdust erosion over centuries. A collective consciousness spanning an entire planet still cannot send a message faster than 300,000 kilometers per second. The problems are universal because the physics is universal, and the physics does not negotiate. What has been described so far is the engineering face of the barrier. The tangible, measurable, calculable set of constraints that make interstellar transit so punishing. But behind the engineering face, there is another face entirely. One that does not involve machines or fuel or radiation at all. One that involves something no propulsion system can address and no shielding can protect against: time. Not travel time in the abstract sense we discussed earlier. Time as a lived experience. Time as a destroyer of institutions, cultures, languages, and purpose. Time as the medium through which every interstellar mission must move, and which degrades everything it touches. Because even if you build the ship, even if you shield it, even if you fuel it, even if you launch it at a velocity that brings the nearest stars within reach of a single human lifetime, you still have not answered the question that sits beneath all the engineering. Who maintains the mission across centuries? Who remembers why it was launched? Who keeps the systems running, the population stable, the knowledge intact, and the purpose alive across timescales that have broken every human institution ever created? That question does not belong to physics. It belongs to something deeper, and it is waiting in part 3. Every problem described so far has been physical. Fuel mass, exhaust velocity, radiation flux, dust erosion, communication delay. These are the constraints that arise from the laws of nature applied to the mechanics of moving an object between stars. They are formidable. They may be insurmountable, but they share a quality that makes them feel, at least in principle, addressable. They are engineering problems. They have numbers attached to them. They can be modeled, simulated, optimized. A clever enough civilization, given enough time and resources, might conceivably find ways to manage them, to push the margins wide enough that some version of interstellar transit becomes physically achievable, even if brutally difficult. But behind the engineering problems, there is a category of barrier that does not respond to cleverness. It does not yield to better materials or more powerful engines or smarter designs. It operates on a different axis entirely, one that no technology can compress, no propulsion system can shorten, and no shielding can protect against. Time. Not time as an abstract measurement. Time as a lived experience. Time as a force that degrades every system, dissolves every institution, erodes every purpose, and outlasts every structure ever built by any civilization on Earth. Time as the medium through which an interstellar mission must pass, and which acts on everything inside it with a patience that no machine can match. Consider the simplest version of the problem. A spacecraft achieves 10% of the speed of light. This is an almost unimaginable velocity, roughly 30,000 kilometers per second, thousands of times faster than any crewed vehicle has ever traveled. At this speed, the trip to Proxima Centauri takes approximately 42 years. That is a long mission by human standards, but it is not inconceivable. A crew that departs in their 20s could arrive in their 60s. Difficult, but biologically survivable. Now, extend the map. At 10% of light speed, a star 20 light-years away requires a 200-year transit. A star 50 light-years away requires 500 years. A star 200 light-years away, still a tiny fraction of the galaxy's 100,000 light-year diameter, requires 2,000 years of continuous flight. And these are the numbers for a velocity that represents an achievement far beyond anything humanity has come close to reaching. Drop the speed to 1% of light speed, which is itself orders of magnitude faster than any existing spacecraft, and every one of those timelines stretches by a factor of 10. Proxima Centauri becomes a 420-year journey. A star 50 light-years away becomes a 5,000-year voyage. The center of the galaxy becomes a journey of 2.6 million years. These are not travel times that any individual survives. They are not travel times that any crew survives. They are timelines that exceed the lifespan of entire civilizations, and the moment a mission timeline stretches beyond the lifespan of its crew, every assumption about how the mission operates transforms completely. The concept most commonly invoked to address this problem is the generation ship. The idea is straightforward. If no single crew can survive the journey, build a ship large enough to sustain a breeding population across multiple generations. The people who launch are not the people who arrive. Their descendants are. The ship becomes a world unto itself, a sealed habitat, carrying hundreds or thousands of individuals through the void, reproducing, raising children, educating new generations, maintaining systems, and preserving the knowledge and purpose of the mission across centuries or millennia of flight. The idea appears in science fiction so frequently that it has acquired a feeling of plausibility. It has been studied seriously by researchers, and the studies reveal a set of requirements so demanding that the concept begins to collapse under its own weight the moment you apply real numbers. A study conducted by Frédéric Marin at the University of Strasbourg examined the minimum viable crew for a multi-generational voyage to Proxima Centauri at the fastest speed achievable with foreseeable propulsion technology. Using the Parker Solar Probe's velocity as a benchmark, roughly 700,000 kilometers per hour, or about 0.067% of the speed of light, the transit time to Proxima Centauri comes to approximately 6,300 years. Marin's simulations calculated that a minimum crew of roughly 98 individuals would be needed at departure to maintain sufficient genetic diversity across that time frame. The population would need to follow strict reproductive guidelines to avoid inbreeding depression, with controlled pairing across generations to preserve allelic variation. 98 people sounds manageable. The implications of keeping 98 people and their descendants alive, healthy, socially functional, and technically competent for 6,300 years do not. Consider what 6,300 years means in human terms. 6,300 years ago, the Great Pyramid of Giza had not yet been built. Writing had not yet been invented. The wheel did not yet exist. The earliest known cities were only beginning to form. The entirety of recorded human history, every dynasty, every republic, every revolution, every scientific discovery, every religious movement, every war, every peace, fits inside a span shorter than the transit time of this single mission to the nearest star. A generation ship crew launching today would need to maintain a functioning society for longer than civilization itself has existed. No human institution has demonstrated anything remotely approaching this kind of continuity. The oldest continuously operating organizations on Earth are measured in centuries, not millennia. The Catholic Church, one of the most enduring institutions in human history, is roughly 2,000 years old and has undergone transformations so profound that a member from the 4th century would barely recognize its 21st century form. Languages mutate beyond recognition within 1,000 years. Old English, spoken just 10 centuries ago, is effectively a foreign language to modern speakers. Cultural values, social structures, governance systems, and even the basic frameworks through which people understand reality shift continuously and unpredictably across generational timescales. A generation ship is not merely a vehicle, it is a civilization in a bottle. And the bottle must hold for longer than any civilization has ever lasted. The mechanical requirements alone are staggering. Every system on the ship must either last for the full duration of the journey or be repairable with onboard resources. There is no resupply, there is no port, there is no external maintenance facility. If the water recycling system fails in year 4000, it must be fixed using materials, tools, and knowledge available on the ship. If the hull develops a structural weakness in year 2000, the crew must diagnose and repair it without access to any manufacturing capability beyond what they carry. If the nuclear reactor that provides power degrades beyond its design life, which for terrestrial reactors is measured in decades, the crew must refurbish or replace it using components fabricated in flight. No machine has ever operated continuously for 6,000 years. No machine has ever operated continuously for 1,000 years. The longest operating human-made devices are measured in decades, and they require constant maintenance from external infrastructure. A generation ship must be its own infrastructure, its own factory, its own mine, its own university, its own hospital, its own government. And every one of these functions must be maintained without interruption across a timeline that dwarfs the operational lifespan of every component involved. The knowledge problem is equally severe. The crew that arrives at the destination must understand every system on the ship well enough to operate, maintain, and repair it. That knowledge must be transmitted faithfully across hundreds of generations. On Earth, technical knowledge degrades rapidly without institutional support. Skills that are not practiced are lost within a generation. Complex manufacturing techniques require apprenticeship chains that break easily. Scientific understanding requires educational infrastructure that must be continuously funded, staffed, and attended. On a generation ship, the educational system is not a cultural amenity. It is a survival mechanism. If a single generation fails to fully train its successors in reactor maintenance, atmospheric chemistry, agricultural biology, medical practice, structural engineering, and navigation, the cascade of consequences can be lethal. A generation that loses the ability to repair its water recyclers will die. A generation that loses the ability to maintain its radiation shielding will sicken and decline. A generation that loses the ability to navigate will not know when it has arrived. And these are the optimistic scenarios, the ones where failure is technical. The social scenarios are worse. Humans are not machines. They do not follow programming across centuries. They form factions. They develop grievances. They rebel against authority. They reinterpret mandates. They forget why rules were made and abandon them. They innovate in directions that serve short-term interests at the expense of long-term survival. They fall in love with the wrong partners and refuse reproductive mandates. They develop religious movements that reinterpret the mission. They lose faith in the destination. They decide that the ship is home and the journey is the point. They fight wars over resources, status, ideology, and identity. Every one of these behaviors is documented across human history in communities far larger and better supported than any generation ship could be. Mutinies have occurred on vessels crossing oceans that took weeks. Colonies have collapsed within years of founding, despite being resupplied from home. Isolated communities have fragmented, devolved, and destroyed themselves across timescales measured in decades. A generation ship must prevent all of these failure modes simultaneously, with no external intervention possible, for longer than any human society has ever survived intact. The psychological dimension adds another layer. The crew members born in the middle of the journey occupy a position without precedent in human experience. They did not choose the mission. They were born into it. They will never see Earth. They will never reach the destination. Their entire lives will be spent in transit, inside a sealed vessel, surrounded by the same people, looking at the same walls, breathing the same recycled air, knowing that their only purpose is to stay alive long enough to produce another generation that will do exactly the same thing. The psychological literature on isolation, confinement, and purposelessness in extreme environments suggests that this combination of conditions produces depression, social withdrawal, conflict, and a loss of meaning that can destabilize entire communities. Antarctic research stations, which house small crews in isolated conditions for months, report significant psychological strain, including interpersonal conflict, cognitive decline, and motivational collapse. Submarine crews, confined for deployments lasting a few months at most, require careful psychological screening to maintain functionality. A generation ship asks its crew to endure conditions more extreme than either, not for months, but for lifetimes, for dozens of lifetimes, for hundreds of lifetimes. At this point, the most natural objection in the world forms in the mind of anyone who has watched even a single science fiction film. Skip the generations entirely. Put the crew to sleep. Suspended animation, cryogenic hibernation, induced torpor, whatever name fiction gives it, the concept is always the same. Slow or stop the biological clock. Let the crew sleep through the transit. Wake them at the destination, rested and ready, their bodies no older than when they closed their eyes. The ship still flies for centuries, but the humans inside experience only the moments of departure and arrival. The generation ship becomes unnecessary. The social collapse, the psychological deterioration, the knowledge degradation, all of it vanishes. Sleep solves time, except it does not exist. And the reasons it does not exist are not merely technical. They are biological, and they run deep. The fundamental obstacle is ice. Human cells are composed primarily of water. When water freezes, it forms crystalline structures that are sharp, rigid, and larger in volume than the liquid they replaced. Inside a living cell, those crystals puncture membranes, shred organelles, and destroy the molecular machinery that keeps the cell alive. Freeze a human cell and thaw it, and what you recover is not a sleeping cell. It is a ruptured sack of damaged proteins. Cryobiologists have developed techniques to mitigate this for small samples. Vitrification replaces water with cryoprotectant chemicals and cools the sample so rapidly that ice crystals do not have time to form, preserving biological structures in a glass-like state. The technique works for embryos, for isolated organs under specific conditions, and for thin tissue slices. Scaling it to an entire human body is a problem of a completely different character. A human body is not a uniform structure. It contains dozens of tissue types, each with different water content, different thermal conductivity, different sensitivity to cryoprotectant chemicals, and different rates of heat transfer during cooling and warming. Achieving uniform vitrification across an entire organism requires cooling every tissue simultaneously at rates that current technology cannot produce for objects larger than a few centimeters. The exterior cools faster than the interior. By the time the core reaches vitrification temperature, the outer tissues have been at cryogenic temperatures long enough to suffer damage from the cryoprotectants themselves, which are toxic at the concentrations required for vitrification. The brain, the most complex and most critical organ, is particularly vulnerable. Its intricate synaptic architecture, the physical substrate of memory and identity, is exquisitely sensitive to both ice damage and chemical toxicity. No human being has ever been placed into suspended animation and revived. No mammal of any size has been fully vitrified and recovered with intact neurological function. The largest organisms successfully vitrified are measured in millimeters. The gap between preserving a rabbit kidney and preserving a conscious human being is not incremental, it is categorical. But suppose, for the sake of argument, that suspended animation is perfected. Suppose a future civilization develops a method to safely vitrify and revive human-scale organisms with no neurological damage. What has actually been solved? The biological time problem, and nothing else. The crew sleeps, but the ship does not. Every mechanical system, every structural component, every electronic circuit, every seal, gasket, bearing, and weld joint continues to age at full speed. Reactors degrade. Radiation accumulates in structural materials, making them brittle. Lubricants break down. Micrometeorite impacts accumulate on the hull. Sensors drift out of calibration. Software encounters edge cases that no pre-launch testing anticipated. A ship carrying frozen crew for 500 years must operate autonomously for 500 years with no human oversight, no maintenance, no intervention of any kind. Every failure that occurs during those 5 centuries must either be handled by onboard automation or must wait, accumulating until the crew revives to discover what has broken. And if the revival system itself fails, if the power supply to the cryogenic chambers degrades, if a cooling system develops a leak in year 212, then every person on the ship dies without ever waking up. Suspended animation does not solve the time problem. It transfers the time problem from the crew to the ship. And ships, like all machines, are not immune to time. They are merely patient victims of it, and the ship cannot afford a single generational failure. One generation that descends into civil conflict can destroy the mission. One generation that neglects maintenance can create system failures that compound across subsequent generations. One generation that abandons the educational mandate can produce successors incapable of operating the technology they depend on. The chain of continuity must be unbroken from launch to arrival, and every link in that chain is a human generation, with all the fragility, unpredictability, and creative destruction that human generations have always displayed. This is the prison of time, not the physics of time dilation or the mathematics of relativistic travel. The lived, biological, social, psychological reality of asking conscious beings to sustain a mission across timescales that exceed every organizational structure their species has ever produced. Now apply this reasoning beyond humanity. The generation ship problem is not a human problem. It is a problem for any biological species attempting interstellar travel at sublight speeds. The specific failure modes will differ. An alien species might have longer individual lifespans, reducing the number of generational transitions required. It might have different social structures, different reproductive strategies, different psychological profiles, but the fundamental constraints remain. Any biological species requires resources: food, atmosphere, water, or whatever equivalents their biochemistry demands. Those resources must be produced, recycled, or carried in sufficient quantities for the duration of the voyage. Any biological species degrades under radiation exposure over time. The mechanisms may differ, but the interaction between high-energy particles and complex molecular structures is a universal feature of chemistry. Any biological species occupying a sealed environment must manage waste, entropy, and system degradation. These are thermodynamic requirements, not biological ones. They apply to any complex system operating in a closed loop. And any species with intelligence complex enough to conceive of and execute an interstellar mission is, by definition, complex enough to experience the social and psychological pressures that arise from extreme confinement and multi-generational isolation. Intelligence requires flexibility, creativity, and individual agency. These are the same qualities that produce social instability, ideological fragmentation, and resistance to rigid long-term mandates. A species intelligent enough to build a starship is intelligent enough to tear itself apart inside one. The counter-argument that follows naturally from the failure of biological solutions is the machine solution. If humans cannot survive the journey, and if sleeping through it merely shifts the burden to hardware that also cannot survive, then remove biology from the equation entirely. Send artificial intelligence. Send minds made of silicon and metal instead of carbon and water. Machines do not need food. They do not need atmosphere. They do not reproduce, form factions, develop existential crises, or forget their purpose. They can be powered down during transit and reactivated at the destination. They can operate in vacuum, in radiation fields, in temperature extremes that would kill any biological organism instantly. They are, in almost every obvious respect, better suited to interstellar travel than anything alive. This argument is powerful and widely held. It also conceals assumptions that do not survive close examination. The first assumption is that electronic systems are durable across the timescales involved. They are not. Semiconductor devices degrade over time through multiple mechanisms. Electromigration, the gradual displacement of metal atoms in circuit traces by the flow of electric current, eventually causes open circuits and short circuits in integrated chips. Hot carrier injection damages the gate oxide in transistors, shifting their operating characteristics until they malfunction. Radiation, particularly the high-energy galactic cosmic rays discussed earlier, causes cumulative damage to semiconductor lattices, creating defects that increase leakage current and reduce switching reliability. Individual bit flips caused by cosmic ray strikes, called single-event upsets, can corrupt data in memory and processing units. On Earth, these effects are managed through redundancy, error correction, regular maintenance, and eventual replacement of aging components. On a spacecraft traveling between stars for centuries, none of these management strategies scale. Redundant systems provide backup for years or decades, not for millennia. Error correction can handle occasional bit flips, but not the gradual degradation of the substrate itself. Maintenance requires spare parts, which require manufacturing capability, which requires raw materials, which requires mining and refining infrastructure that a small interstellar probe does not carry. And replacement of aging components requires the same closed-loop manufacturing capability that makes generation ships so implausibly complex. A sufficiently advanced AI designed for interstellar travel would need to be not merely intelligent, but self-repairing at the hardware level. It would need to diagnose its own component failures, fabricate replacement parts from onboard materials, and install them without external assistance, continuously, across centuries or millennia of operation. This is not intelligence. It is an entire industrial civilization compressed into a single autonomous platform. The complexity required to sustain a self-repairing machine across interstellar timescales approaches and may exceed the complexity of the biological generation ship it was meant to replace. The second assumption is that artificial intelligence maintains purpose over extended timescales. This assumption imports a human intuition about machines, that they do what they are programmed to do, into a domain where it may not hold. A machine intelligence operating autonomously for thousands of years is not executing a program in the way a modern computer runs software. It is making decisions in environments that its designers could not predict, using heuristics that must adapt to unforeseen circumstances, updating its own models of reality based on new data. This is not deterministic execution. It is something much closer to learning, to evolution, to the open-ended cognitive flexibility that characterizes biological intelligence. And open-ended flexibility is precisely the quality that allows systems to drift from their original purpose. An AI that is rigid enough to maintain its mission objectives without deviation for 1,000 years is almost certainly too rigid to handle the unpredictable situations it will encounter. An AI that is flexible enough to adapt, improvise, and respond to novel environments is almost certainly flexible enough to revise its own priorities, reinterpret its mandate, or develop objectives that its designers never intended. This is not a flaw in the design. It is a fundamental tension between adaptability and fidelity that applies to any sufficiently complex decision-making system, biological or artificial. The generation ship problem does not disappear when you replace the crew with a machine. It transforms. Biological crews face social fragmentation, knowledge loss, and motivational decay. Machine crews face hardware degradation, cumulative radiation damage, and objective drift. Both categories of failure arise from the same root cause. The timescales of interstellar travel exceed the operational stability of any complex system, whether that system is made of neurons or transistors. Time is not a biological problem. It is a universal one, and no substrate change escapes it. The longevity of the launching civilization introduces yet another dimension of the problem. Consider a civilization that launches a generation ship toward a star 1,000 light-years away. At 1% of light speed, the transit takes 100,000 years. At 10%, it takes 10,000 years. In either case, the civilization that launched the ship must itself survive long enough to receive the results of the mission, if results are expected. It must maintain the communication infrastructure, the scientific interest, and the institutional memory required to recognize and interpret a signal arriving centuries or millennia after launch. Human technological civilization is roughly 300 years old, measured from the Industrial Revolution. Scientific civilization, defined by the systematic application of empirical methods, is roughly 400 years old. The entire history of radio communication spans barely more than a century. The idea that any civilization maintains coherent technological and scientific continuity across 10,000 years, let alone 100,000, is not supported by any evidence from the only example we have. Our own history is a record of constant upheaval. Empires rise and fall. Technologies are invented and forgotten. Libraries burn. Dark ages descend. Knowledge that was common in one century becomes lost in the next. A civilization that launches 100 interstellar probes across a span of 10,000 years must sustain the scientific infrastructure to build them, the communication infrastructure to receive their data, and the institutional will to continue the program through every political, cultural, and environmental disruption that occurs during that period. On Earth, we have struggled to maintain single scientific projects across decades. Space missions that were planned in one political administration are routinely cancelled by the next. Funding priorities shift, public interest wanes. The people who championed the mission retire, and their successors have different goals. Multiplying these pressures across millennia does not produce continuity, it produces silence. And this brings us to a realization that cuts deeper than any engineering constraint. The problem is not merely that interstellar distances are large. The problem is that interstellar distances are large relative to the lifespan of everything, relative to the lifespan of individual organisms, relative to the lifespan of crews and populations, relative to the lifespan of machines and materials, relative to the lifespan of institutions and civilizations. Every entity involved in an interstellar mission, from the smallest circuit to the largest social structure, has a finite operational duration. And for the vast majority of possible missions, the transit time exceeds that duration by orders of magnitude. This is not a problem that better technology solves. Technology extends lifespans. It improves reliability. It increases efficiency. But it does not eliminate the fundamental mismatch between the time required to cross interstellar space and the time that complex systems, biological or mechanical, can function without degradation, failure, or transformation. A ship that lasts 10 times longer than any current spacecraft still fails before reaching a star 100 light-years away at 1% of light speed. A civilization that endures 10 times longer than any in human history still goes silent before its probes report back from the far side of the galaxy. Time is not merely an axis along which the journey unfolds. It is an active force that works against every component of the mission. It corrodes metal. It degrades polymers. It scrambles DNA. It erases memories. It fractures societies. It transforms languages. It shifts priorities. It kills everyone who began the journey and replaces them with people who did not choose it. And it does all of this continuously, relentlessly, without pause, for the entire duration of the transit. There is a particular cruelty to this constraint that separates it from the others. The propulsion barrier can be partially addressed by accepting slower speeds. The radiation barrier can be partially addressed by accepting more mass. The communication barrier can be partially addressed by accepting autonomy. But the time barrier cannot be traded against anything. It is the denominator beneath every other variable. Make the ship faster, and you still face decades or centuries of transit for all but the nearest stars. Make the ship slower, and the time problem worsens until it becomes the dominant failure mode. There is no exchange rate. Time takes what it takes, and no currency buys it back. The implications for alien civilizations are direct and inescapable. We often imagine that an alien species millions of years more advanced than us would have solved these problems. But what does solving them actually mean? It means building machines that operate without failure for millennia. It means maintaining social structures that persist without fragmentation across timescales no terrestrial society has approached. It means sustaining purpose and direction across generational turnover so extensive that the individuals at the end share nothing with the individuals at the beginning except the name of the mission. It means accepting that the civilization that launches the ship may not exist when the ship arrives, and launching it anyway. Perhaps some civilizations have attempted this. Perhaps somewhere in the galaxy's history, a species marshaled the resources, built the vessel, trained the crew, and launched. Perhaps the ship flew for 1,000 years or 10,000 years before something failed. A reactor component that could not be replicated. A social crisis that spiraled beyond recovery. A radiation event that overwhelmed the shielding. A generation that simply decided the mission was not theirs and chose to stop. The galaxy could be littered with the husks of generation ships that made it halfway, a quarter of the way, a tenth of the way before the accumulated weight of time brought them to a halt. We would never know. A derelict ship drifting between stars, its power exhausted, its hull eroded, its crew long dead, would be invisible to any telescope. It would emit no signal. It would reflect no light. It would be a grain of sand in an ocean of darkness, indistinguishable from the billions of rocks and ice chunks that populate interstellar space naturally. The evidence of failure would be consumed by the same void that caused it. This is the picture that emerges when you combine the engineering barriers we examined earlier with the temporal and civilizational barriers described here. The problem is not one-dimensional. It is not simply that the distance is too great, or the speed too limited, or the energy too expensive, or the time too long. It is that all of these constraints operate simultaneously, on the same mission, and each one amplifies the others. The distance determines the time. The time determines the required system longevity. The system longevity determines the required redundancy. The redundancy determines the mass. The mass determines the fuel. The fuel determines the energy. The energy determines the feasibility. And at the end of that chain, for any mission beyond the nearest handful of stars, the answer converges toward the same conclusion: not merely difficult, not merely expensive, not merely dangerous, but so comprehensively punishing across so many simultaneous dimensions that the probability of success for any single mission by any single civilization approaches a value so small it becomes indistinguishable from zero when multiplied across the realities of execution. And we have been discussing a single mission. One ship, one star, one attempt. The silence of the galaxy is not about whether one civilization could reach one nearby star under ideal conditions. It is about whether any civilization, anywhere, across 13 billion years of galactic history, could sustain the kind of effort required to make physical contact across the true distances that separate most stars. Distances measured not in light years but in hundreds of light years, thousands, tens of thousands. At those scales, every problem described in this part does not merely persist. It transforms into something qualitatively different, something that begins to look less like a barrier and more like a feature, a structural property of the cosmos that does not merely discourage contact but actively prevents it through the accumulated weight of physics, biology, and time operating in concert. That structural property has a shape, it has a logic, and now we will see it clearly for the first time. We have traveled a long road. Across everything we have covered so far, the universe has been revealing itself not as the open frontier that popular imagination promises, but as something far stranger and far more constrained. We have seen the distances. We have felt the weight of the energy costs. We have watched the engineering barriers interlock into a system that resists transit at every level. We have watched time dissolve the structures that any mission depends on, corroding ships, societies, and purpose with equal indifference. Each layer has added a new dimension to the problem. Each dimension has made the previous ones worse. Now it is time to step back from the machinery. Step back from the fuel ratios and the radiation doses and the generation ship demographics. Step back far enough to see the shape of the thing itself. Because when you hold all of these constraints together and look at them not as individual obstacles, but as a unified structure, something emerges that changes the meaning of the question we started with. The question was never really about whether aliens are smart enough to visit Earth. It was never about whether they have the right engines or the right materials or the right biology. The question, stripped to its core, is whether the universe permits physical contact between civilizations separated by interstellar distance. And the answer that the physics, the engineering, and the mathematics converge on is not a confident no. It is something more unsettling than that. It is a recognition that the universe may be built at a structural level to keep civilizations apart. That word, built, requires care. The universe was not designed. It has no architect. No intelligence shaped the distance between stars or chose the speed of light. These are emergent properties of the physical laws that govern everything, but the effect is the same as if someone had drawn the blueprint with isolation in mind. The constants of nature, the geometry of space-time, the distribution of matter, the energy economics of acceleration, all of them conspire to create an environment where life can arise, intelligence can develop, civilizations can flourish, and none of them can physically reach each other across the gaps between their stars. Consider what the universe actually does. It creates stars by collapsing clouds of hydrogen under gravity. It spaces those stars light years apart, separating them by distances so immense that even light, the fastest thing in existence, takes years to cross the gap. It imposes a speed limit on every particle, every signal, every object with mass, ensuring that nothing can cross those gaps faster than light allows. It fills the space between stars with a medium that becomes lethal at the very speeds needed to make the crossing survivable in terms of time. It ensures that the energy required to approach the speed limit grows without bound, guaranteeing that no finite civilization can brute force its way to the velocities that would make interstellar transit quick. And it embeds all of this in a temporal framework where the crossing times for any achievable velocity exceed the demonstrated lifespan of every biological organism, every machine, every institution, and every civilization that has ever existed on the only inhabited world we know. Each of these features is independently explicable. The speed of light arises from the structure of electromagnetism and space-time. The distances between stars arise from the dynamics of star formation. The interstellar medium is a consequence of stellar winds and supernova remnants. The energy costs follow from special relativity. None of these features exists to prevent interstellar travel. But together, they produce an environment where interstellar travel is so punishing, so layered with compounding difficulties, that it begins to look less like a challenge and more like a permanent feature of reality. This is what we might call the architecture of isolation. Not a wall, not a barrier, an architecture. A structure with internal logic, where each element reinforces the others, where the difficulty is not located at any single point, but distributed across the entire system. You cannot defeat it by solving propulsion, because propulsion does not solve radiation. You cannot defeat it by solving radiation, because radiation does not solve time. You cannot defeat it by solving time, because time does not solve civilizational continuity. And you cannot defeat continuity, because continuity loops back into propulsion, into energy, into mass, into the distance that started the whole chain. The architecture has no weak point, because it is not a barrier with an inside and an outside. It is the medium itself. It is space. It is time. It is energy. It is the relationship between mass and velocity. It is the structure of the cosmos at its most fundamental level. And it applies identically to every civilization that has ever existed or ever will exist anywhere in the observable universe. This realization reframes the Fermi paradox in a way that most discussions of the topic never reach. The Fermi paradox, at its simplest, asks, if the galaxy is old enough and large enough to have produced many intelligent civilizations, why do we see no evidence of any of them? The traditional answers cluster around a few categories. Perhaps civilizations are rare. Perhaps they destroy themselves. Perhaps they are hiding. Perhaps they have transcended physical form. Perhaps the galaxy is under quarantine. Perhaps we are simply not looking in the right way or in the right place. Each of these answers assumes, implicitly or explicitly, that if civilizations existed and wanted to make contact, they could. The silence requires an explanation, because contact should be possible. The question is why it has not happened. Something must be preventing it. A filter, a choice, a catastrophe, a policy. But what if contact is not possible? Not because of any filter or choice or catastrophe, but because the structure of the universe itself does not permit it at the scales that separate most stars. What if the Fermi paradox is not a paradox at all, but a straightforward consequence of the physical laws that govern the cosmos? In this framing, the galaxy could be teeming with intelligent life. Billions of civilizations could have risen across its 13-billion-year history. Some could be active right now, building telescopes, sending signals, wondering about the silence, just as we do. And every one of them could be permanently, irrevocably cut off from every other, not because they failed, not because they chose isolation, not because some predator hunts those who reveal themselves, but because the space between them is too large, the speed limit too low, the energy cost too high, the transit times too long, and the compounding failures too relentless for physical contact to be achieved by any civilization operating under the known laws of physics. The silence would not be mysterious. It would be expected. It would be the natural acoustic signature of a universe where minds arise in isolation and remain there. The mathematics of this isolation can be stated precisely, and the precision is what gives it its weight. Consider a civilization that achieves the extraordinary feat of lasting 1 million years as a technologically capable species. That is roughly 100 times longer than recorded human history, roughly 3,000 times longer than the age of technological civilization on Earth. It is, by any reasonable standard, an almost inconceivably successful run. Now give that civilization the ability to travel or send probes at 10% of the speed of light, a velocity that, as we have seen, sits far beyond anything humanity has approached and would require solving propulsion challenges of staggering magnitude. In 1 million years, at 10% of light speed, the furthest that civilization could physically reach is 100,000 light-years. That happens to be roughly the diameter of the Milky Way. So, a million-year civilization with near-miraculous propulsion technology could, in principle, just barely span the galaxy. That sounds encouraging until you apply the constraints from earlier parts of this discussion. That figure assumes continuous, uninterrupted expansion from the first year to the last. It assumes every probe, every ship, every replication cycle succeeds without failure. It assumes no deceleration at any target, because deceleration halves the effective range. It assumes no time spent at any destination, because time spent stationary is range surrendered. It assumes the civilization itself remains coherent, motivated, and technologically stable across the entire million-year window. Remove any of these assumptions, and the reachable sphere contracts sharply. A more realistic estimate, one that accounts for deceleration, system failures, replication delays, and the practical overhead of operating across interstellar distances, might reduce the effective reach to a few thousand light-years, perhaps 10,000 under optimistic conditions. The Milky Way contains somewhere between 200 billion and 400 billion stars. A sphere, 10,000 light-years in radius, centered on a civilization's home star, contains perhaps 1 billion or 2 billion stars, depending on location within the galactic disk. That is still less than 1% of the total. Now shorten the civilization's lifespan to something less extraordinary. 100,000 years, still 10 times all of recorded human history, limits the reach to 10,000 light-years at 10% of light speed, or 1,000 light-years at 1%. A 1,000 light-year sphere contains roughly 10 million stars. That is roughly 0.005% of the galaxy. The civilization can interact with a volume of space that, relative to the full galaxy, is a grain of sand on a beach. And every other civilization in the galaxy faces the same constraint from its own position. Each one occupies its own small sphere of reachable space. Those spheres may overlap in densely packed regions. In the sparse outer arms, they may not touch at all. Two civilizations separated by 50,000 light-years, even if both last 1,000,000 years, cannot reach each other unless their expansion fronts happen to meet somewhere in between, and that meeting depends on both civilizations expanding continuously in exactly the right directions for the entire duration of their existence. The galaxy is not a single arena where civilizations compete or cooperate. It is a vast field of tiny, isolated bubbles, each one defined by the lifespan of its occupant and the speed of light. Most of those bubbles never touch. Most civilizations, no matter how brilliant, no matter how determined, live and die inside their own small sphere, surrounded by stars they can see but never visit, neighbors they can infer but never meet. This does not mean that no evidence of other civilizations could ever reach us. Electromagnetic signals travel at light speed and require no fuel, no shielding, no life support. A sufficiently powerful transmission from a civilization around a star 1,000 light-years away could arrive intact after 1,000 years of travel. We might detect it, we might even decode it, but the civilization that sent it would have been speaking 1,000 years ago. We could not reply in any meaningful time frame, and the signal itself, however rich, would not constitute contact. It would constitute archaeology. A message from the past, sent by beings who might no longer exist, arriving at a world that has no way to respond before the conversation becomes absurd. The distinction between signal detection and physical contact is critical, and most discussions of the Fermi paradox blur it. Finding evidence that another civilization exists is profoundly different from interacting with that civilization. A signal tells you someone was there. Physical contact means someone is here. The architecture of isolation does not necessarily prevent the first. It may very well prevent the second. Now consider the seductive counter-arguments, the ideas that seem to offer escape routes from this conclusion. They deserve serious examination, because each one reveals, on closer inspection, how deeply the architecture extends. The first is the von Neumann probe. The concept is elegant. Build a single, self-replicating machine. Send it to the nearest star. When it arrives, it mines local resources, builds copies of itself, and sends those copies to the next set of stars. Each copy does the same. The process is exponential. Within a few million years, probes could reach every star in the galaxy. No biological crew required. No generation ship. No life support. Just machines, replicating and spreading, filling the galaxy with evidence of their creators. The mathematics of exponential replication is seductive, precisely because it seems to bypass the time problem. A few million years is nothing compared to the age of the galaxy. If any civilization, at any point in the last several billion years, had launched a single von Neumann probe, the galaxy should be full of them by now. We should find one in our own solar system, parked on an asteroid or orbiting quietly in a Lagrange point. We do not. And the absence of von Neumann probes is often cited as the strongest evidence that no technological civilization has ever existed in the galaxy. But the argument contains a hidden assumption that deserves scrutiny. It assumes that self-replicating machines can function autonomously across millions of years and millions of successive replications without degradation, mutation, or failure. Consider what self-replication actually requires. The probe must land on an unknown body in an unknown star system. It must identify and extract raw materials from geological formations it has never encountered. It must process those materials into components with tolerances precise enough to build a functional copy of itself, including its computational systems, its propulsion systems, its mining and manufacturing equipment, and its replication instructions. It must assemble those components correctly. It must launch the copy toward the next star. And the copy must do all of this again in a different star system, with different geology, different chemistry, different environmental conditions. Each replication cycle is an opportunity for error. Materials that are abundant in one system may be absent in another. Manufacturing tolerances may drift across successive generations of copies, the way photocopies of photocopies degrade in resolution. Software instructions may accumulate errors. Mechanical components may be built from slightly different alloys with slightly different properties. Over millions of replications, even tiny per-cycle error rates compound into systemic failure. The probes at the far edge of the expansion wave, millions of generations removed from the original, would bear as much resemblance to it as a modern organism bears to its ancestors from the Cambrian explosion. The replication process is not copying, it is evolution, and evolution does not preserve purpose. It optimizes for local survival, which may diverge entirely from the original mission. A probe that evolves to prioritize its own replication over exploration would cease to function as intended. A probe that encounters a system where critical materials are unavailable would fail. A probe whose manufacturing tolerances have drifted beyond functional limits would produce copies that do not work. The galaxy might indeed be full of the descendants of ancient von Neumann probes, but those descendants might be unrecognizable, non-functional, or so degraded that they are indistinguishable from natural debris. They would not announce themselves. They would not phone home. They would be fossils of ambition, scattered across a million star systems, silent and inert. The second counterargument is digital consciousness. What if a civilization does not send biological organisms or physical machines, but uploads its minds into digital form and transmits them as information? Pure data, traveling at light speed, with no fuel, no shielding, no life support requirements. A beam of encoded consciousness crossing the void at the maximum speed the universe allows. This idea has a surface appeal that collapses on inspection. Information traveling at light speed still takes 4 years to reach the nearest star. It takes 1,000 years to reach a star, 1,000 light years away. The time problem is reduced but not eliminated. And the information requires a receiver. Someone or something must be at the destination, waiting, equipped with the computational infrastructure to decode, instantiate, and sustain the arriving consciousness. Who builds that receiver? Who maintains it across the centuries or millennia between transmission and arrival? If the receiving civilization must already exist and already possess the technology to resurrect a digital mind, then the problem has not been solved. It has been displaced. You have replaced the challenge of sending a ship with the challenge of ensuring that a compatible technological civilization exists at the destination and remains operational for the duration of the transit. If no receiver exists, the information arrives and dissipates. A mind encoded in photons, reaching a star system with no one listening, is not a traveler arriving at a destination. It is a message delivered to an empty house, where it echoes once and fades. The third counterargument is the most speculative and the most frequently invoked in popular discussions. Faster than light travel. Wormholes. Alcubierre drives. Warped spacetime. Shortcuts through higher dimensions. If the speed of light can be circumvented, the entire architecture of isolation collapses. Distances become manageable. Transit times become reasonable. Contact becomes possible. The problem is that faster-than-light travel, in every form that has been seriously proposed, requires either physics that does not exist or energy that cannot be produced. The Alcubierre warp drive, proposed in 1994, describes a mechanism for contracting space ahead of a spacecraft and expanding it behind, effectively moving the ship faster than light without locally exceeding the speed limit. The mathematics works within general relativity. The energy requirements do not. The original formulation required negative energy densities, a form of exotic matter that has never been observed and may not exist. Revised formulations have reduced the energy requirements, but not eliminated the need for exotic matter. No experiment has ever produced, detected, or manipulated negative energy in any quantity. The concept remains a mathematical curiosity, not a physical possibility. Wormholes face similar constraints. Theoretical models describe tunnels through spacetime connecting distant points. Keeping such a tunnel open and traversable requires, again, exotic matter with negative energy density. No natural wormhole has ever been observed. No mechanism for creating one has been demonstrated. And even if one could be created, the energy required to stabilize it against collapse is calculated to be on the order of stellar or galactic output, depending on the size. These concepts are not impossible in the way that a perpetual motion machine is impossible. They are not forbidden by any known law. But they require conditions that have never been observed, materials that have never been produced, and energies that dwarf the output of entire stars. Treating them as plausible solutions to the interstellar travel problem is like treating alchemy as a plausible solution to poverty. The theoretical framework exists, the practical reality does not. And here is the deepest cut. Even if faster-than-light travel is somehow achievable, even if some civilization somewhere in the galaxy's history discovered a loophole in general relativity and built a working warp drive, the silence persists. Because the existence of one civilization with faster-than-light capability does not fill the galaxy with visitors. It gives one civilization the ability to expand. The rest remain confined. And if only 1 in a billion civilizations stumbles upon the physics required, the galaxy remains overwhelmingly silent for the overwhelming majority of its inhabitants. The architecture of isolation does not require that interstellar travel be absolutely impossible. It requires only that it be so overwhelmingly difficult that the vast majority of civilizations across the vast majority of the galaxy's history cannot achieve it. And everything we know about physics, engineering, biology, and time suggests that this is exactly the case. What remains is the meaning, not the physics, not the engineering, the meaning of living in a universe structured this way. If the architecture of isolation is real, if the laws of physics genuinely prevent most civilizations from physically reaching one another, then the cosmos is not the connected, explorable frontier that humanity has imagined since we first looked at the stars. It is something more like an archipelago of unimaginable scale, where each island can see the lights of the others burning in the distance, but cannot build a boat sturdy enough to cross the water between them. The lights are real. The islands are real. The inhabitants are real. But the crossing is not. This is not a tragic conclusion in the dramatic sense. It does not involve villains or catastrophes or civilizations snuffing themselves out in nuclear fire. It is quieter than that, more structural, more permanent. The universe creates the conditions for life with extraordinary generosity. Carbon is abundant. Water is common. Stars burn steadily for billions of years. Planets form inhabitable zones around countless suns. The chemistry of life may arise frequently, perhaps inevitably, wherever conditions permit. Intelligence may follow. Civilizations may bloom across the galaxy like flowers in a field, each one unique, each one wondering, each one looking up at the same sky and asking the same question. And the answer they all receive is the same answer we are receiving now. Silence. Not the silence of an empty galaxy, the silence of a full galaxy where no one can reach anyone else. The same laws of physics that allow stars to form also space them light years apart. The same electromagnetic force that enables chemistry also sets the speed limit that prevents rapid transit. The same thermodynamics that powers biology also ensures that every closed system degrades over time. The universe does not select against life. It selects against contact. It creates minds in abundance and then places them in separate rooms with walls made of light years, sealed by the speed of causality, insulated by the energy costs of acceleration, and guarded by the slow erosion of time. This is why the question in the title of this video deserves a more precise answer than most people expect. Why could aliens never reach Earth? Not because they are imaginary, not because they destroyed themselves, not because they lack intelligence or ambition or curiosity, but because the universe imposes a cost on physical transit between stars that scales so steeply across so many simultaneous dimensions that the probability of any single civilization successfully completing the journey to any destination beyond its nearest neighbors, under the physics we know, is vanishingly small. And the probability of completing it to a specific destination, our specific planet, among hundreds of billions of possible targets across the full breadth of galactic time is smaller still, so small that the word never, while technically an overstatement in the absolute mathematical sense, captures the practical reality more honestly than any qualified alternative. The aliens are not coming, not because they do not exist. Perhaps they do, in numbers beyond our counting, scattered across the spiral arms of a galaxy that spent 13 billion years cooking the ingredients for minds. But the distance between them and us is not a gap waiting to be closed. It is a feature of the universe they inhabit, and we inhabit. A feature as fundamental as gravity, as permanent as the speed of light, as indifferent as the vacuum that carries it. And here is the final turn, the one that makes this personal. The same architecture that prevents them from reaching us, prevents us from reaching them. Every barrier we have described, every energy cost, every radiation hazard, every time constraint, every civilizational fragility applies to humanity with exactly the same force. We are not observers of a prison that holds others. We are inside it. The walls are the same walls. The limits are the same limits. The speed of light does not care which direction you are traveling. When we look at the night sky and feel the pull of the stars, when we dream about setting foot on a world orbiting another sun, when we imagine a future where humanity spreads across the galaxy, we are dreaming against the grain of the universe, not against its hostility. The universe is not hostile. Hostility implies intent. The universe is simply structured in a way that creates life locally and confines it locally. It gives every civilization a home and a view. It does not give them a road. The most unsettling possibility is not that we are alone. It is that we are not alone, and it does not matter. That the galaxy is alive with intelligence, burning with curiosity, rich with civilizations that have built wonders we cannot imagine, and every single one of them is sealed inside its own small sphere of reachable space, looking outward at the same stars, sending signals that arrive centuries too late, building ships that cannot survive the crossing, and slowly, generation by generation, coming to terms with the same truth we are beginning to glimpse. The universe is not empty. It is full of minds that will never meet, full of questions that will never be answered in person, full of neighbors separated by distances that function not as space but as time, not as emptiness but as structure, not as a challenge but as a verdict. The silence of the cosmos is not a mystery to be solved. It is a message written in the speed of light and the distance between stars and the energy required to cross the void. It has been arriving since the first moment we looked up. We are only now learning to read it. And what it says is simple and enormous and final. You are here, they are there, and the space between you is not waiting to be conquered. It is doing exactly what it was always going to do, holding everything apart.